nueva edición del seminario. Creo que podemos comenzar ya. Well, it's a big pleasure for me to introduce you, Professor Alfio Botsi. Alfio is a big friend of us, especially with me, because we have a nice history of working together. I was part of his group during my postdoctoral research, so it's a long friendship. Alfio now it's holder of the chair number 9 in Wuerzburg University, which is focused on scientific computing. And Alfio is a relevant researcher, one of the most important regarding the application of multigrid algorithms to optimization, computational optimization, and now he's a little bit switch from multigrid to another applications. I think these Hamiltonian algorithms, and this is something new that also for me. So it's a big pleasure to have this talk now and let us learn how this Hamiltonian approach. So Alfio,
okay,
and this is your
okay. Thank you,
audience
Sergio.
now.
Muchas gracias. As you said, bienvenido a todos. Yeah, benvenuti a tutti. So I'm Alfio Borzì. I'm Italian, and I guess we could try to speak also Italian or Spanish. I'm very happy that Sergio asked me to give this talk. We have many times talked of my visit to Quito, but these have never been possible. I see Juan Carlos is possible. Oh, Juan Carlos, nice to see you. So thank you very much for this invitation. Muchas gracias. It's a big pleasure for me to be at least virtually in Quito. I hope sometimes in the future this will be a real, will be by a real presence in and to see your city and your place. Anyway, so I'm sorry, I try not to make too long, so I will start my talk. But please let me tell you that I'm very happy if you interrupt me, if you have questions. And even later or another day, I'm very happy to communicate with you, to share ideas and impressions. Okay. So what I would like to do, what I suggested for a seminar is something that is, say, my new passion. As Sergio said, first I was working with multigrid, then I've worked a long time with Fokker-Planck equations, stochastic models, and things are coming together. Actually, there are many links on the topics I've worked in the last 10 years. Even if these links are not so apparent, they come at some point. And about the Pontryagins maximum principle and a method to use this to solve control problems. So let me share with you my slides, okay? If you want, I can send you the slides later so that you can use them anytime, okay? So now I have to understand how to share it, yeah? I think I know, I should try somewhere there's a share screen, right? So
yes, in share screen, I think it's possible.
Yes. So here is it. Now I don't know if you see only the slide or you see myself in the slide. Okay.
You can exactly. That's perfect.
Yes. Okay. You see this? Yeah.
Yes.
Okay. So well. Okay. So let me tell about this, and I explained the name. Why sequential quadratic Hamiltonian? So this name has been coined by me and my previous PhD student, Tim Breitenbach. In fact, most of this work started with the PhD of Tim Breitenbach, who is now working in the research center of SAP in Germany for optimization problems. So he preferred to go to industry, but he was very good in mathematical analysis and so. So what is the motivation of this work and why I think it can be interesting for you? although you already are all expert of optimal control and optimization with PDEs, I think this is a little something new. I hope so, and in some way, I wish that this is something towards the future. Yeah, the future of research in this field. So one point is that we are all confronted since, say, uh, 10 years or so with working with control problems that are non-smooth, yes? But we take care of having convex functionals, continuous function, Lipschitz continuous functionals, so that at least we can do our semi-smooth analysis, and we have powerful methods like semi-smooth Newton methods, but also some multi-grid methods like I worked with Sergio times ago. Anyway, but if you start asking, what happens if the functional is non-convex or is even discontinuous, then there is not so much around, and maybe it's time to approach this issue. So this question is very much related to the possibility to give an answer. If you can, if you want as a mathematician to talk about something, you wanted to express, to state the existence of this something, or the existence of an optimal control also. So this is a special point that has been discussed very long by Young in his book. So it is about existence. And if we can talk about existence, then we can start discussing computation of this object. Yeah. Okay. And when I discuss this, then it comes to the point that I can decide, or I have to decide, if I can characterize this existing object as in terms of optimality system, which we usually use the Lagrange approach, is about differentiation. For sure, we have extended the concept of differentiation from classical one, from classical Frechet derivatives to sub-differential calculus. But what is beyond that, no? So at least I'll try to look at this direction. And then if we have a consistent framework for existence and characterization, then the question is if you can construct a method that puts these things together. Okay. So what I'm going to discuss is not the answer to this, is the starting of discussion on this. And this quadratic method is the attempt to do this. Okay. So let me show you something that you know very well. Do you hear me? Yes, you. I don't know if you have switched the microphone. That's the point with the online discussion, that at some point I ask if you hear me.
Yeah,
It's okay.
It's okay. So that's also going on with the lectures. I give the lecture online, and at some point I'm not sure if. Okay, so
same feeling.
Yes. So let us look at this slide. Yeah, this slide, you see a classical control problem for a semi-linear parabolic problem. So you have the parabolic operator, the derivative in time minus Laplace y, and then you have some structure for the nonlinearity of the mechanism of control. It can be just linear, so f of x, y, u is just z, y, u is u. So it's a linear control, or it can be bilinear, y times u, or more complicated, okay? But this is not essential at this point. But just to say, let's talk about problems like this, and you have some admissible control set. And just at this point, I would like to mention that one part of our modeling work is to decide what is the control cost. I mean, the function of the control and the functional. So this function G And one other thing is about the admissible set of values that the control can take. And well, at this point, the decision becomes restricted very much by what we can do theoretically. I mean, numerically, one can try everything, but to make sense, what we took here in G is something which is a continuous function. Okay, so Lipschitz continuous function. And the K of U, the set of the values of the control, is a convex set. Okay, so I'm trying to discuss what we can say and do if this is not the case. Yeah, for example, let's take this G. This G, for example, this G here, okay, this is not convex. It is like a double potential. And if I add this term here, the second term, beta, absolute value of U, etc., it is discontinuous, no? If you have this shift here, this switch. So indeed, you think this G is inside the integral, okay? Or you have the, say, a semi-smooth function, which is quadratic plus absolute value, okay? So we still know everything about this G of U, but we don't know much about this. So why I put this G of U? Well, this G of U historically is two things that I want to discuss. The first one, the non-convexity, is a long-standing problem that has been discussed by Young, okay? Lawrence Young, in his book, discuss in fact this, and this is what brings us to the Young measures. So it extends the notion of optimal control from a function to measures, and it gives a clear characterization about existence, a characterization of controls that satisfy such problems with this kind of functionals. So we have a theory that says, yes, there exists something, okay? In fact, in the book of Young, at some point he's quoting Hilbert, and Hilbert says, there is always a solution. The point is to define what a solution is, okay? So this is what brings us to Young measures. But in the approach of Young, there is at least one condition for G, that it cannot be discontinuous, okay? So it can be non-convex, but continuous. And what I would like to discuss also is the case where we have a discontinuity. At this point, the theory of Young is also cannot be applied. And in fact, the functional is no more weakly lower semi-continuous. And whatever we know about optimization, proof of existence, I mean, you know the theory of the approach of Tonelli, no? The Tonelli approach to the minimum sequence, and then you prove if you have a reflexive Banach space, then there is some convergent subsequence, etc., etc. This approach cannot be done because the functional is no more weakly lower semi-continuous. Okay, so it is the barrier to discuss about this is not to write this slide. No, I mean, I can write G whatever I like. The point is I can make sense of it. Okay, so it is about existence of optimal controls. As I said, in the standard, I mean, let's say modern approach that we know, we have this control to state map. So given a control, we analyze the map, which is the solution of our PDE for a given U. We define this control to state map. We usually prove that this map is continuous. And to do the Lagrange approach, we need also to prove Fecha differentiation. Then we look at the classical, say, optimization problem, even if infinite dimensional, of minimizing this reduced functional, where the constraint, the differential constraint is included. And then the steps that we do are prove that this functional is weakly lower semi-continuous. Then following Tonelli, we have this minimizing sequence. We prove there is a convergence subsequence. And then we prove if there is some non-bilinearity, some strong convergence of the function y, etc. I mean, these things you know very well, okay? And at this point, we also use that OAD need to be weakly sequential compact, so we have some closedness and convex property, okay? So this is just to remember what we usually do, at least what I learned, yeah? So, but what happens if we are not in the case where this can be applied? Okay, this is just my question, no? And I would be happy to learn any comment from you or suggestion how to extend this list, etc. So the non-convex case actually has been studied in many different ways by many different mathematicians or other scientists with many different ideas. Some ideas are ad hoc for a given problem. There are classical papers by Cellina or Toland. Then there's a more general framework, which is the so-called relaxed controls. This is has been introduced by Young in the context of calculus of variation, but he already was giving examples of control. And then Varga wrote a book which is all about relaxed controls with ODEs. I must say that there are very few works with PDEs. So there is a very open field already at this point about control measures, okay? And there are some cases where KU is not KU, so the values that the control can take are not, the set is not convex. One special case that you for sure you have heard about it, or you have already worked on it, is the mixed integer programming problem. Yeah? So you have a control of a PDE, but your control can take discrete values. So this is not a convex set, and people try to solve this with differentiation. Yeah? And I would like to explain, to do something different, okay? And then there is, I would say, the way out of any problem. If you are not in this case, I mean, you say you're just discontinuous. So there is no subdifferential calculus, no measures, no Young measures, no ad hoc solution. We are still, we have a place where you can survive. This is the variational principle of Ekeland. The variational principle of Ekeland does not require weakly lower semi-continuity, just lower semi-continuity, boundedness from below, but then the concept of control is more, say, more weak, yeah? So in fact, what Ekeland proves is that if you have a function lower semi-continuous bounded from below, then it is always possible to prove existence. Suboptimal means that since the functional is bounded from below, you have an inf for this function in your set, okay? Then you take this inf and you sum any epsilon greater than 0, any. Then the theorem, I mean, the main point result of Ekeland is to prove that there is always a function U bar in this set which makes j of hat smaller than this. So if you actually think what we do numerically, for example, where just this epsilon can be confused with the approximation of quadrature, then actually we are always computing suboptimal solutions. But let's say this is the most general approach to discuss existence of solution or minimization problem, okay? And this is a very general framework. It applies to the infinite dimensional case. And in fact, there are results in many cases, especially in calculus of variation. All what I've mentioned is more, there are more results than in the control theory, okay? So let me say that now I am happy to talk about you, because for all functional that I'm showing you, there is some concept of existence of solutions, okay? So this is, and I will talk just a few of them, and because this is ongoing work, and well, I will be happy to in the future to show you more. Some result is already done. I will mention at the end. Okay. Okay. So let me show you another few issues. Okay, if we think of our control problem I showed you before, the parabolic, no, let's continue with it. So the next step to in our standard framework is to write a Lagrange function. And in the Lagrange function, I will have the part which is the functional, now is space-time, because Z there was the functional xt, space and time, okay? And then we have a Lagrange multiplier and we have our differential constraint, as you are used to do. Am I right that I'm supposing that all your group is doing control problems, or is any, should I explain this more in detail? I don't know. I guess you are all expert of this.
Not everyone right now. So there's a
Okay.
good part that already understands that, but not everyone.
Okay, but PDEs, yes, yeah, PDE, yeah, differential models and
It
so on.
is an optimization to some
Okay.
extent, yeah.
Okay, so for those who do optimization but not control, maybe they do calculus of variation. These ideas are always, they all come in calculus of variation. So it's not a waste of time, okay? In fact, is the challenge is to make a minimization of, say, discontinuous function. There are problems in elasticity with discontinuous phenomena, material properties, fractions. So actually, this topic, I mean, like the Young measure, so you can find there as well. And for those who do just numerics of PDEs, it is also the challenge to solve a PDE with some discontinuity. And this is what we are going to discuss as well, okay? And one of the challenge in numerical analysis is that once I have this Lagrange function, assuming I can write an optimal system, so let's say the derivative of our function must be zero, if you don't have constraints. So we actually have to solve three objects together, coupled together. One is our equation, the parabolic, then they have the adjoint equation, and a variational inequality, which becomes equality if the UAD is, I mean, if I can take any function in my control space, okay? But what I want to point out here is that there is, at the level of deriving this optimal system, when I write this optimal system, I have to make some derivatives. You see that here we have a derivative of f with respect to y. F was the semi-linear part, the, say, non-linearity part in our PDE. So if this function is not differentiable, then we get the first problem here, okay? And this is a topic that discussing this maybe if f is the absolute value of y or something like this, no? Then we can do something with semi-smooth calculus. But my focus today is that when we write the third part of the optimal system, we have to make derivatives with respect to u, to the control function or the optimization function of the cost of the control and of the non-linearity of the PDE. And this is the point where I cannot use my control function g discontinuous. So this will not make any sense, okay? And also I cannot have a discontinuity in the PDE with respect to u, because also this will not make any sense, okay? So this is what now we are doing when we talk about the Pontryagin maximum principle. So actually this is a story that goes back to the 1950s. So, I mean, I've read this story probably. There is a nice article by Pesh, or one nice article by, how's the guy there, the American guy? Sussman. Okay, so there is the story of optimal control theory, and there is it is the Cold War. So from one side we have the Rand Institute with Bellman, Isaacs, and Egenes, etc. And the other side we have Pontryagin, Podyarsky, Gamerlitz, etc. So in other words, both people work about optimal control with ODE systems, and both people have the same problem ahead, but they come out with two different approaches to compute them. One, they say from the west side, comes directly from the calculus of variation, from Weierstrass, Lagrange, etc. So they write the optimality system like this one, like this you see now, okay? So there is a derivative with respect to the control to write the optimality system complete. But in Pontryagin, if you want, there is a slight difference. So in Pontryagin, the idea is that you have the same optimal system. In fact, the idea of a joint equation as we use it today comes from a work from Pontryagin, actually, historically, okay? The difference is that in Pontryagin, coming directly from the Legendre condition, the characterization of the control is that at any point of where your system is defined, a function which we call Hamiltonian, I call it Hamilton-Pontryagin function, is considering that the other functions are the optimal ones, is maximum at that point with the optimal control value, okay? In fact, this condition of maximizing it, if we can make a derivative with respect to u, the characterization of this maximum is the derivative that I wrote to you here. So if you want, Pontryagin takes a derivative less, take the integral, okay, if you want. Instead of taking the characterization of the maximum, it takes the maximum itself as a statement for optimality. I don't know if it's clear what I'm trying to say, no? So if you do a study of a function and you have the point of maximum, then the first you say, okay, the point is where the derivative is 0, no? And then you have to look at the second derivative to see if it is max or min, yeah? If you have these derivatives. But suppose you have a cusp, then exactly there you don't have a derivative. So what you do, already we have done in the school, if derivative there is not, then you take the value of the function and look at that value, and you can see if it is max or min. Exactly this is the point of the maximum principle. You look at the maximum of this Pontryagin function. If I take the derivative of this function h, with to u, I get okay. And as you see, in case of constraints, this variational inequality is exactly the characterization of the maximum of this function h in a constraint set, okay? But notice that this constraint set is not UAD, it is the k, the value of the set where the control has its values, okay? So it's some interval or a discrete set, okay? So the Pontryagin maximum principle characterizes the optimal control by the state equation, which is the equation of our model, the adjoint equation again, and if this u is a control, so it's a necessary condition, if it is a control, then this function h is maximum at that point. As you see, I'm saying here minimum because I write less or equal, because I take the Lagrange function with the minus sign, okay? I mean, I have a minus sign, okay? It's just I'm mixing the things because it's sometimes it seems more, for many people, more useful to talk about mean. So if you want, I'm talking about the minimum principle. It's just a question of changing the sign of the Hamiltonian, okay? So in many books you find this with less or equal or the other way around. But what is important to see is that here at any point of your domain, you are taking you are evaluating the functional h at the optimal value. And here the same, but not the variable control that you are searching in the admissible set of values, okay? I think this is the most important slide to explain you that what I'm going to do now, okay? So as you see, we can use the maximum principle with our codes. In fact, we compute the equation, the adjoint equation, but now we look at the Hamiltonian. And this is a function that we look at any point in our space domain, space-time domain, whatever. Okay? Okay. Now, I don't want to complicate this discussion, but to prove this, why we call it principle and not theorem, because this must be proved for any class of problem. Exactly as you prove it for the Lagrange framework, you have to prove this is control to state map is differentiable, this function is differentiable, etc. In Pontryagins, you have to prove that this condition, theorem 1, holds for your problem. So the way to prove it is by a variational approach, which is slightly different from the Lagrange approach. The point is that the variation is now so-called the needle variation. So you want actually to make changes in a larger space. Okay, so you just take the L2 variation of U. So you have, if U is a reference function, you keep the same U, and at some point, a small interval, you make a change. This is a so-called needle variation. And with this type of calculus, you prove something very useful. You prove that if you take the difference of your functional with this varied u and with the optimal u, yeah, obtained from the varied u, then this kind of derivative, let's call it Weierstrass derivative, okay? This derivative is exactly given by the difference of the value of the Hamiltonians with respect to the value of the function on the needle, on this point, yeah? Okay, this is a local change. So this means that if you take your function and you just change the u, and this is needle point, this very small change, and make the limit with the, say, the area of this change, yeah, this support of this function, then this is exactly the difference of the two Hamiltonian with this change of the function. I hope I explained you this. Anyway, the principle is the way to prove is by this needle variation, okay? And at least for the problems I show you now, this can be done in all these cases. Yeah, and this, you find in Pontryagins with ODEs, it's more common to see this. A good reference for the PDE case, one of the very few references for the PDE case are the book of Lee and Young. Okay, it's a very nice book. There are a lot of work result in this book, but still very specialized. And there is a very nice paper by Raymond and Zidani, which is about the parabolic case I'm showing you, okay, where they do needle variation to prove that this principle is a theorem, okay? This is the point, yeah? Okay, so just to mention that if we are in the worst case scenario, the functional is discontinuous, then as I told you, the only way to prove existence of suboptimal solution is by Ekeland variational principle. And in fact, one can prove that the characterization of this suboptimal solution for a given epsilon is characterized by a similar, say, statement of the Pontryagins principle. The Hamiltonian is less or equal the Hamiltonian for a general V plus this epsilon. So you essentially get the same result reflected in the Hamiltonian. So the Pontryagin principle applies with this change, okay? So we can also characterize this suboptimal solution within the framework of Pontryagin, okay? So this is, well, I put the reference, you will find this in the file. Okay, so what we are going to do now? Now we are approaching this method, yeah? So the point is that, and this was already done by Krylov and Chernusco immediately, actually, a few years after Pontryagin, Gamerlitz and Boltiansky wrote the book, the famous book on Pontryagin maximum principle. You say, okay, if this is so, then let's try this. I solve the problem with a given U. I compute the adjoint. Then I take the Hamiltonian with this actual approximation that I have. I minimize or maximize the value of the Hamiltonian at each point, and I get a new control function, okay? And then I recompute forward the adjoint. It is, if you want, like doing the gradient approach, but you don't do the global gradient change, but you go in any point that try put the gradient equal 0, okay? Something like this is more or less. So the problem is that, and this method may work, depends on convexity, choice of numerical parameters, but it is for sure not robust. So it is easy to make it diverge, okay? But already Chernusco and Krylov give a name, the successive approximation method, SA method. Successive approximation is what they call it, okay? So this method was published in a few papers, then there was no more continuation on this, but especially because the Russian colleagues were more on the theoretical side, okay? But then almost 20 years later, there were two colleagues from Japan, Shindo and Sakawa, who said, oh, if we put penalization of the change of this control on any point, then we can control this blow up and get something more robust. And this is what Shindo Sakawa did in the 80s, okay? So you see now we are taking the Hamiltonian and we are putting a quadratic penalization of it, okay? So the word quadratic comes now, quadratic, okay? Keep this name. And the point is that when Shindo and Sakawa did this, they could prove and also implement for ODEs, okay, for small ODEs, where every time they changed U, they recomputed the entire state function, etc. So if you try to do this method in PDEs, it will take forever, yeah? But anyway, that was Shindo Sakawa. This method also was only used by Shindo Sakawa, and it closed there, okay? Till, well, let me say that until I, Tim Breitenbach and myself tried to do this with PDEs. So the idea is that if you want to do this with PDEs, you have to avoid to compute the state function at any space-time point where you change the control. You want to finish the update and then recompute, no? The method worked immediately, but there was not, the theory was not applicable. The convergence theory that already Sakawa did, it was, say, retaken by Bonanz. But this theory is based on the idea of recomputing every time. So the main point that we did was to revise this theory to prove that if this epsilon is taken sufficiently large, then you don't need to update y while you are updating u, but you can do this afterward, and you prove a convergence result, okay? And since the successive approximation method was also the name used by people to explain the Picard iteration in ODEs, we decided that it is good to have a new name. And this is why we call it sequential quadratic Hamiltonian. So sequential, we do sequentially, point by point, update the Hamiltonian. Hamiltonian is what we use, and quadratic because we have the parallelization. So now you have discovered that the sequential quadratic Hamiltonian method is the name we gave, okay? It seems a very nice name, so thinking of other sequential quadratic algorithms seems to fit with the others. Okay, so the main ingredients are augmented Hamiltonian with a quadratic term. Obviously, could be another penalization. And the importance is to prove that this method is converging, is robust with respect to all parameters, optimization and numerical parameters. And at the very end, it must be fast. Otherwise, it's only a curiosity, no? So this is what is the method. I mean, this is not very interesting slide, but it's essentially a loop. You compute your state and joint variables for the given u. Then you go through the augmented Hamiltonian. You find another u, which locally the value of this u is the maximum or minimum of this augmented Hamiltonian. Okay, so you make a suite is like Gauss-Seidel method. Then what you need for the convergence is to prove that you have a reduction of the functional, and this is done in this way. If there is no sufficient decrease, you increase epsilon. Okay, you say, I'm not happy with this new update. I increase epsilon. What it means increase? Well, actually, you increase penalization, so you will you try for lesser change. And the interesting fact is that you can prove that doing this way, there is an epsilon such that you get the sufficient decrease. This is the most important, say, new result that we have, okay? So I make you a few examples with linear, then non-linear. I think I will go through with this, maybe not too slow, okay? I don't know about the time. Yeah, okay. So if I have a simple elliptic problem with a linear control, here I have L1 differentiation. So as you see, for me, having L1 or L2 or L0 doesn't make any difference because I'm looking at this, not at the functional, but at the function H, at this function here. So this is a scalar function, okay, at that point. And minimizing a function also with the absolute value is no issue. I mean, we compute also analytically, okay? In fact, in many cases we do it. So this will be the H1 case, and you see maybe typical results. You have some constraints, you have some sparsity, okay? So this is a very fast computation with very few okay? But this is functional is still a continuous function, yeah? So let's take a discontinuous functional. So discontinuous functional is just this function g of u. It is doing nothing if the value of u is below a certain threshold. Otherwise, it's switching on like a L1 function, okay? So this can be, say, if you want to solve an inverse problem where you try not to influence the control, you can give a threshold where you don't do anything, you don't do regularization. Also, in this case, computing the Hamiltonian minima at any point is a method of doing two lines of computation on the paper and then implement it. Yeah, so you get something like this. You see that from this picture that this S I've written here is 20. You see this lower part. This is exactly the part of 20 of this, where the S is starting, and this is about the constraint, which is 100 here. So this is a very different control problem now that cannot be considered directly by other methods, unless you do some regularization or convexification. There are obviously other ways to approach it if you modify it, okay? Okay, but it is not fun, yeah? Okay, so the same thing, parabolic with the discontinuous functional. You see, you say, but writing the Hamiltonian is very easy. First of all, this part is not, is there just for aesthetics, for beauty, because you optimize only on the control variable, so the value of y doesn't matter. It's like a constant in the point, it doesn't matter. It is about getting the max or min of this function on the grid point, okay? So it's a scalar function of u, of the value u. It is the value of the control at that point, okay? So it's very easy to write. The augmented is to put this quadratic part, okay? And this is another point. So I would like to track a tracking of a trajectory. This is like this function here, and finding the control with this discontinuous functional I wrote here before is the same as the other one. So, and you get things like this, okay? Okay, so let me say, we don't have gradients, so how we can test if we are doing well or not, no? Well, the only way is to look at the maximum principle. The maximum principle says, in the solution we have found, if the solution is optimal, then the H is the max that you get at that point, or the min that you get at the point. So what we do is to verify this fact, the difference between the actual H we found by the method after we go out of the sequential quadratic scheme, and the one where we take the values again and we recompute the max and min on that point, yeah? And you can see that for different mesh, by different tolerance or stopping criteria, as the tolerance becomes more strict and strict, they say the percentage of points where this criteria is satisfied to machine precision is 99.98% or things like this. So it's essentially everywhere, okay? So this is the way we come out to verify the quality of the optimality of this point by the Pontryagin principle. Additional result, I mean, I'm just trying to pick out from this paper with Breitenbach the essential point. There are issues. The first is, but when you do this pointwise change, are you sure you get a measurable function? Well, the answer is yes, in general, if the function k is, say, a convex function, okay? Even if ku does not need to be convex. In the case of functions which are discontinuous, the answer in general is no, but case by case can be yes. So for the G I showed you, the answer is yes. The result of this U, the switching from point to another, no? This is not the case. So for this case, we have that the U is measurable. So we are working with functions that at the continuous level are well defined in the iterative process. As I told you, in many cases, you can even compute the minimum or maximum at that point analytically. This is what we did for the discontinuous case. So you actually don't compute anything. You just get two candidates. You verify the value of the Hamiltonian, these two candidates, and choose the right one. And so the square scheme is very fast. I mean, I'm talking about 10, 20 iterations to get to a solution. But the essential point I told you was, are we sure that if you increase the penalization, the quadratic pair, then we can minimize, we can find a U that minimizes the functional? The answer is yes. One can prove that an equality like this is possible, which means that as far as there exists a theta, so a finite number, So if I take epsilon bigger than this theta, and this is what the algorithm is searching, then I get this negative and multiplied by this term, so I get the required reduction I want. Okay, so this is the essential point to prove that this quadratic SQH scheme is converging in a finite number of steps. Okay. Okay, so there are additional results about the monotonically decrease of the functional, the fact that this control tend to go 0, and very important, in the case where we have also the Lagrange framework, we can prove that we converge to the same point, assuming we have at least locally we start the same convex situation. We can also have some sufficient condition for decrease that can be proved a priori for some functional. But okay, let me skip this part. These details are all in the paper, the first paper we published with the SQL. So similar result with bilinear controls. Bilinear in this sense, or linear affine, means that the control can multiply the state. And I guess I'm talking already from 40. Do you have 5 minutes more? Yeah.
Yeah, 5 minutes. Okay.
Okay. So
Yes.
bilinear is also a way. This is a very nice experiment because we put everything together. We have the quadratic case, the L1 case, the L0 norm, and we have also the discontinuous part. Okay, it's a funny way. This is a quantum control problem in the sense that the matrix A and B are taken from a spin, from a quantum spin problem, so quantum mechanics. And there are many experiments. So this is without the discontinuity. So delta is 0, if I remember well. Yes, delta is 0, and also gamma is 0. So L0 norm is not here. So it's just L2, L1. And you see, in fact, the sparsity increases by increasing the sparsity coefficient beta. And you see the percentage of point where the Pontryagin principle is satisfied. There is also a comparison with the semi-smooth Newton. So this is CPU time to solve the same problem and the number of iterations. But it gets more funny if now I switch on the L0 norm. So it's gamma here. So you get these very nice strange patterns. So you see still the L1 effect, but you see also L0 norm effect is coming here. And to the end, I switch on the discontinuity functional. So now you see that where the discontinuity soil is, S is 10, this is scaled by 100. So this is exactly the 10 limit. You see the other functional is doing something and you get these nice pictures, okay? So this for fun. So you can have all functionals of this that can be implemented in this framework. Okay, just not to annoy you, you can also look at this. There are the similar experiment with PDEs. So with this. And let me tell you that if you have a mixed integer control problem, the best way to do it is by Pontryagin, because in the Pontryagin, you just need to go through the discrete points of your set. So if I have Ku is just these numbers, you just, at the point where you are optimizing your Hamilton-Pontryagin function, you just check these points, yeah? So you can see that here the control takes values in this set. There is no need to make, or to try to make derivatives that cannot be done because this set is not convex. There is no open set here to define a derivative, okay? So mixed integer programming problem could be more investigated in this framework. And it is also possible to do state constraint problems. Here we have used the result by Daniel Wachsmuth and Veronica Karl that to do some regularization to solve state constraint problems with this sort of penalization here. And the details are in the second paper we wrote about this SQH. In fact, in the second paper, the one, the SQH method, we present all this problem, P1, P2, P6, and we provide also the codes. So you can get all these codes, they are available if you want to try. And okay, I think I have to stop here. Did I forgot some? Well, this is the case where we have not enough theory, when we have L1 of the tracking term, but we have good results. And I wanted to talk about control of stochastic models. In fact, if we describe all trajectories by the probability function, we come up with a Fokker-Planck equation. And there is a connection between open loop optimal control, Fokker-Planck, Hamilton-Jacobi-Bellman equation, and Pontryagins. And this is the result of this paper just appeared only a few months ago. I just give you the reference and I stop here. So this is about open and closed loop control. Where is the paper? I mentioned it, I don't find it. At some point must be, okay, anyway, you find it here. I'm sure I've mentioned it. So that's it. And there are a lot more about this. For the moment, there are applications with inverse problems, parameter identification, photoacoustic tomography, and also in the Young framework of Young measures. The SQH method seems to work also in that case. Okay, thank you very much. That's it, yeah.
Thank you, Alfio. It was a very interesting talk, and I'm sure that it would be questions. So this is the time for questions, comments, please, colleagues.
So, may I start?
Yeah, of course, of course.
Yes.
You got frozen a little bit, just.
I'm sorry?
You got frozen, but now you're.
Oh, yeah, okay. I'm alive again.
Yeah.
So
Okay.
it's very nice to see you, Alfio, and
yes,
very
me
nice
too,
talk.
yeah.
I'm very glad to have you here in this seminar. But you know, I have a couple of mathematical questions concerning your talk.
Sure,
And,
yeah. Actually, I did wrong that I closed the slides. I have to reopen them. But go on with the question.
yeah, no, I mean, the first question is a very natural one. Is concerning the discontinuity of the functional. So things
Yes.
may get very wild for simple examples of discontinuous functions.
Yes.
So my question in that respect is, first of all, what can you prove concerning, I mean, what kind of assumptions do you have to make for G? Which kind of discontinuities? I mean, a limited number of switching points or things like that for the things
As
to go
far
well?
as, yes, the theoretical point is that it must be a lower semi-continuous function.
Okay.
So the discontinuous function I've used always, it is lower semi-continuous. So this is just a switch in the functional sense. This is lower semi-continuous function. The integral is LSC, and then first of all the theory of Ekeland applies. The theorem of Ekeland applies, and also the results about say well-posedness of the method do also use lower semi-continuity, and that's it. Actually, there are no other assumption. Yes, the boundedness from below.
But for the convergence of the method itself, do you need something there, or?
So the issue of convergence, I think I'm very optimistic in expressing it, in the sense that so the following results are given by this G lower semi-continuous, okay? But this integral of G lower semi. The first result is the one I showed you, that in a finite number of steps, you can find a penalization such that the resulting control makes a minimizing step of the function, okay? This step requires only lower semi-continuity.
Mhm.
Okay. If we talk about convergence to a point, so first we have to say which point is this. If we have only lower semi-continuity, I don't have convergence in the sense that there is also no point to prove. I mean, the Ekeland theory tells you that there are suboptimal solutions and they can be infinite number of them. So they cannot be a convergence in that sense. But if I take a function which is weakly lower semi-continuous, so let's say L2, L1, then yes, we have the proof of convergence to the point that characterizes this minimum. Okay, so it depends in which situation we are.
Okay.
Yeah.
Okay. Thank you. So I come back with another question afterwards, but I think there are more people.
Yeah, no, go on,
to ask
go on.
something.
You're welcome. Yeah.
We have a question from Sophia. Sophia, would you like to pose your question, please?
Hi, Alfio. I have a question.
Hello, Sophia. Yes.
Hi. Regarding to the augmented Hamiltonian. Well, I don't work with optimal control problems, so I'm sorry, this is a silly question. But what would you lose if you don't use a quadratic penalization in the augmented Hamiltonian? Or what would be the benefit of using another penalization, or it's just whatever? I mean, you can use whatever penalization.
Yes. So without penalization, we are at the original work of Krylov and Chernusco. This means that if the discretization of the problem is not fine enough, if the weight of the optimization are too small or things like this. I mean, in all places where you are not very clearly convex, yeah, this local update will diverge. It is like you try to solve a Helmholtz problem with a Gauss-Seidel method when we are close to an eigenvalue, okay? It's you are far away from a convexity and your update can be too big and bring you in another place, okay? So
Okay.
just saying generally. The other question, yes, you are right. It must not be quadratic. It must be a convex penalization. I mean, something that increases when you go away from the point where you're starting your change. Yeah. Okay. So it can be also L1. It can be L difference to the power 4, or something else that you like. Okay.
Okay. Thank you.
Yes, you are welcome. Yeah.
So building on that, Alfio, so if you get an L1 penalization, for instance, you get this exact penalization, would that improve somehow something?
Actually, we tried L1, but for the numerical, say, convergence behavior, I cannot explain better this. It was better to use a quadratic penalization.
Okay.
Yeah, we tried, but we couldn't see any advantage in getting that. Yeah, in having L1.
Do we have more questions?
I have one. Hi, Alfio, thank you for your nice talk.
Thank you.
Very interesting. But I concerning to the state constraints, you somehow add some regularization of the
Yes.
state constraint, right?
Yes. Yes.
But in the case that, for instance, it is usual that when you have a state constraints, the adjoint state it has low regularity. So does this affects to the overall performance of the algorithm somehow?
Well, lower regularity, yes, but we are now talking at the numerical level, yeah.
Yes, okay. Because your Hamiltonian will depends on P, right? And
yes,
somehow
I'm checking to show you again. Can I show you this? The share screen again. So in some sense, you you are regularizing the constraint, yeah?
Okay, so you replace you don't have the
No,
adjoint.
you have not the hard constraint, the real one.
Okay, okay.
And okay, the point is the following. We tried to make it directly, as you say, no? as you are
Yes.
asking. Right?
Yes.
Yeah. The point is that when we do this, that we change a control everywhere, in the philosophy of the SQH, we would change U everywhere and then recompute Y, then the state constraint will not be satisfied. Okay? So, because in some sense, you do local changes that will influence your state in a global sense, no? So it is difficult to get this control point by point. So the way we tried is to take this, say, approach by Waxmuth to make this regularization of the state constraint, okay, where this rho is increasing, so you cool down to the state constraint, the real state constraint problem, okay, and then in this way the update of the sequential quadratic method is working properly, okay, in the sense that we do not how say verletzen, we do not I mean, we satisfy the state constraint in all iterations. Okay, so the direct approaches you mentioned does not work in this way at the moment, unless we learn more about how to change the control U pointwise, so that Y remains feasible. Say. Okay.
I see. Okay, thank you. Another small question concerning with the quadratic penalization. You have this epsilon that somehow reminds me to the augmented Lagrangian or proximal method.
Yes.
I don't know. Do you have to choose this carefully? Is it difficult to choose this parameter? Or?
No, not at all. This is the adaptive working of the code. I mean, I want to show you again the algorithm. I should be somewhere before. Oh, where is it? Sorry, I have to look myself. Yeah, here. So this is the epsilon is adaptively computed at every global step of the control. Yeah. So if epsilon, the present epsilon does not give me a sufficient decrease of the functional, it is increased by a factor sigma. You see the sigma bigger than 1? Then I increase epsilon and I repeat my update of U with the augmented Hamiltonian with this new epsilon. If this decrease is obtained, then I reducing epsilon again by a factor zeta, which is something 0.1 factor, okay? So it is not at all difficult. Sure, the choice of sigma and the z are something you have to play with, but usually we take 0.1 or 1.1. So a little more than 1 or something a little smaller than 1. So you want increase or decrease. It is more or less when you do the Armigio condition, how you choose, you know, there is a factor lambda or a term.
Okay.
Yes, something like this. So
okay.
it's more experience. If there is an optimal one, I don't know. We just take 1.1 to be bigger than 1 and 0.9 to be smaller than 1, because the theory is done in this sense.
Okay, I see. Thank you.
Yeah, you're welcome.
So do we have more questions, more comments?
Sergio, I have a question. Oh, I'm Paula.
Dale, Pau. Dale.
Yeah. Hi, Alfio. Very nice talk. Please,
Hello,
we have the. Let me show me. We have the slides here. Can you please put in the 33 in the page 33? I think.
33.
Yeah.
Page 33. So it's one of the last.
Yeah, I think it's.
This one.
this one, the mixed integer optimal problem. You say that if you have this admissible set that it's not convex, it's like just number, I said.
Yes,
that, like,
these numbers, yes.
Yeah, but what would be the strategy if you have like a finite, but a very, very large, very large elements in these sets, in these admissible sets?
You have to go through them. Yes.
For all of them?
Yes, because well, unless you have a knowledge a priori around which value you are, yes. Yes, you have to go through all of them.
Okay.
Yeah. But I don't know such problems. I mean, usually this should be a big set, actually.
Okay.
I usually see binary problems like -1, 0, 1, or things like this. So like switching, you know. But I'm not doing any special application. So this is just to show you what we do, yeah. But
Okay.
you are right. If there is the set is there are infinite, countably many points, then it will be forever. Yeah.
Yeah. Thanks.
Sure. Yeah.
Okay. More questions? More comments?
But can I mention to Paula to answer to add a comment? There is one point that I should like to stress again. Since you have the Hamiltonian function, it's a real function. It's a function of one variable in this case. No, I mean it can be also a vector, it can be two-dimensional, whatever control. But let's say it's a scalar function, okay? So you have a one function of a scalar variable. So it is in many cases the fact that you can see the minimum, the formula for the minimum by hand. So even if you have an infinite set of discrete points, yeah, it is very likely that if you know the function g, your optimism, I mean your setting, and you look at this scalar function, you analytically have the formula that tells you what is the discrete point that you have to pick.
Okay.
Okay. So I even think that we could try an infinite set. That would be very interesting, very challenging. Yeah? It probably gets a very easy solution also in that case. If we choose some G that we can manage in some point. Yeah. Yeah.
Okay.
So do we have more questions, comments?
Hi, Sergio. Hi,
Hi,
Sergio.
David.
Just a small one. I'm interested on the this last slide when you were trying to do the absolute value instead of the squared.
Okay. This one.
What are the challenges that you have to make, with the changes that you have to make on the Hamiltonian in order to make it work, or do you have problems with existence in that case, or?
No, the challenge is not in the Hamiltonian. The challenge is in the adjoint variable. The challenge is to construct the adjoint variable, because for the Hamiltonian is irrelevant whatever y is, because c it looks only at the control. But when you have a non-differentiable functional in y, then what is the adjoint? Yeah, I mean there is a way to approximate it by semi-smooth calculus, but I'm not sure that I mean especially there is one or two works by Christian Claesson who has done something in this direction, but this is still a topic, say, somehow open, especially also in the numerical point of view, how to implement something like this in a PDE. So this is a non-smooth PDE, the adjoint. Yeah, yes, this is a very nice point. If we could remove this problem, then we need no differentiability at all.
Correct.
Of all our things. Yeah, no differentiability.
Yeah. That's quite interesting. Thank you for the nice talk.
You are welcome, David.
Okay. So more questions, more comments. I think. Okay, cool. If not the case, Alfio, thanks again. It was a very,
I thank you. It was very nice. Yeah, I
big
like
pleasure to have you here, and the talk
My
was
pleasure.
great, and it was a nice discussion. Anyways, as Alfio told us, he's going to provide us the slides and also some references. So I will let you. I will send you, of course, and I put in this OneDrive file that we have with all the information of the seminar. Thank you, Alf, again.
Okay.
It was very nice to see you. Please
Yes,
keep
it
healthy.
was my pleasure. I thank you very much for this opportunity. It was nice to see your group. I'm very happy that Juan Carlos could also join because I know he has a lot to do. I mean, I must say you are doing a very nice job. I mean, you have a very nice center with a lot of activity, and I would be very happy to exchange with you more frequently. So thank you very much for this opportunity, and let's see for the next time. Yeah.
Thank you, Alfio.
Okay.
Thank you.
And gracias a todos por
Buonasera,
venir.
arrivederci.
Cuídense.
Grazie.
Ciao,
Grazie mille.
grazie. Muchas
Have a good-
gracias. Yeah.
Bye.
Hasta la vista. Ciao.
Ciao.
Adiós.